no holes in it, and shirt with a collar, no holes in it?
It's good.
Okay.
There's actually 4 holes in the shirt.
It wasn't from San Francisco. Just wanted to look that up. It's one of these officers, Jered. It was somewhere you were late. What
How is he?
Not gonna work.
Is everyone ready or?
Is it gonna work? Yeah,
You might need to save the note.
that's, it might, I don't know. There's a folder under my something, go to my documents and 328, 329 up there. Put it section. Now, let me show you a secret now. You see what he's doing? Hitting this tape. Want to know a secret? How to do that real
F5.
quick? Don't have to use a mouse?
F5.
F5. I said F5. Hey, hit escape. F5. Sweet. There you go. And if you turn it off, it becomes a flashlight.
Hello, my name
Anybody want one of those, you can get them at Ace Hardware, that's $7 or $8.
Hello, my name's Jered. I'm a member of the Gold Team along with Jered, Jason, and Simon. And today I will be presenting the steady state operating curve and step response for the voltage station between 70 and 95 volts. Today I will be covering system details, experimental observations, and a summary of the results. The chart on the projected right here is a schematic of how the system works. The voltage is input into a computer and travels into a voltage controller. From the voltage controller, it goes to a 5 horsepower 3-phase motor. And from the motor, it travels into the generator, and the generator sends the voltage into a light bulb and a voltage transmitter. The voltage transmitter then sends the voltage back to the computer. Right here is a block diagram of the voltage system. The power is input in a percentage in the motor, and it travels to the generator, and the generator outputs a voltage. The picture on the top is a picture of the motor, and the power from the motor travels through a shaft into the generator it's coupled with. And on the bottom, these are the load lights, and this is the power supply to the motor. This is a sample graph for an 83% power input. There is a 72% steady state voltage, and the standard deviation is plus or minus 0.3 volts. The table shows the values we used in our range from 83% power input to 95% power input, with the mean volts on the steady state and 2 times the standard deviation. And the formulas over here are how we calculated the data. This is our steady state operating curve, which is over our entire range, because we have a high percentage of power input. It's steady state the entire time. Sticking with the 83% power input, this is a sample graph. The change in the output was 3.50 volts, and the change in the input was 2%. To calculate the gain, we took the change in the output divided by the change in the input, which gave a gain of 1.95 volts. per percent. The time constant was calculated by finding the time constant was calculated to be 0.7 volts, or 0.7 seconds, and it was found from the time that it took for the signal from the input to reach, or to get response from the output.
That's what you call, let's say, 0.07.
0.07 seconds.
That's what you meant?
Yeah.
Okay.
And then the time constant was calculated is 63.2% from the initial input, or the initial output value to the steady state value. And that was found to be it was found to be 3.50 volts. No, sorry about that. The time constant was found to be 0.25 seconds. This is a summary of all our results from 83% to 94%. The chart shows the average gain, the uncertainty, and whether or not the step was up or down. The next chart is the same summary, just for the dead time, with all the same calculations. And the last chart has the average time constant for all our tested values, the uncertainty, and whether or not the step was up or down. In a summary, our curve was from 83 to 95% was the operating range. We used a 2% response, and for each step up and step down, we calculated the gain, the standard deviation, and we did the same for the time constant and the dead time.